Okay, let's dive right into this. Welcome, everyone. Listen, if you are sitting down for your Cambridge Computer Science exams, specifically the AS and A-level syllabus 9618, you already know the pressure is absolutely on. I mean, picture it. You're in the exam hall, you flip the page, and you stare down an 8-mark extended response question on factors affecting computer performance, specifically cache memory. And what happens? You freeze. Or even worse, you furiously write half a page, walk out of that hall feeling like an absolute genius, and then later on realize you scored a 3 out of 8. Ouch. So why does this happen? Well, the difference between a B and an A star in syllabus 9618 often comes down to one absolutely fundamental shift in your mindset. You've got to stop acting like a student trying to frantically recall a textbook, and you need to start acting like a paleontologist. Now, you might be wondering, what on earth do I mean by that? Think about it. A paleontologist doesn't just find a random bone in the dirt and instantly guess what the entire dinosaur looked like, right? No, they carefully dig through the fossil layers, they examine the environment, they understand the specific context of where they are digging, and they systematically reconstruct the full picture piece by piece. And honestly, that is exactly what you need to do with these complex Cambridge exam questions. It's like a giant puzzle, and you need all the pieces.
So the core question we really have to answer today is this: what actually separates that B grade from an A star? Top students don't just memorize the basic difference between level 1 and level 2 cache. I mean, that is just baseline knowledge. If you're coming up from the IGCSE or O-level syllabuses, like 0417, 0478, 0983, 0984, or even 2210, you might be totally used to simply stating facts and getting the marks. But at the 9618 A level, no way, that doesn't cut it anymore. You have to act like our paleontologist. You must reconstruct the full answer by applying theoretical concepts to completely unfamiliar, highly specific contexts. The examiner is going to throw a scenario at you. Maybe it's a real-time air traffic control system, or maybe it's a high-frequency algorithmic trading server, and they will ask you to evaluate cache performance in that exact setting. A B student just states what cache is, but an A-star student, they analyze exactly how spatial and temporal locality directly impact the hit rate in that specific high-frequency trading server scenario. That's the game changer.
To get you operating at that A-star level, we are going to journey right through the examiner's playbook today. Here's our quick roadmap for this explainer. First up, we'll uncover the performance grade gap and look at the biggest traps you need to avoid. Then we'll establish the core cache principles. Third, I'm going to reveal the method mark strategy. Fourth, we'll expose the top 3 examiner warnings pulled straight from Cambridge. Fifth, we'll tackle critical analysis and evaluation. And finally, stick around because I'm going to give you the final hack, a custom memory framework to absolutely guarantee you hit all the assessment objectives. All right, let's jump straight into section 1, the performance grade gap. We need to identify exactly where students are losing marks. When principal examiners sit down to mark thousands upon thousands of papers, they notice very clear patterns. The gap between a passing grade and a top-tier grade usually comes down to 2 distinct traps, and I want you to ask yourself which one of these you might be. On the left side of your screen, we have Alex. Now, Alex has spent countless hours memorizing the textbook. When asked a question about how increasing cache size affects performance, Alex panics and just dumps every single raw computer science fact onto the page. Alex talks about SRAM, DRAM, clock speeds, and even throws in the von Neumann architecture for good measure. But guess what? Alex scores poorly. Why? Because there is absolutely zero contextual analysis. Alex just didn't answer the specific question that was actually asked. Then, on the right, we have Sam. Sam is constantly panicking about the ticking clock. Sam rushes the answer, sees the magic word cache, and hurriedly writes down, cache makes the computer faster because it's physically closer to the CPU, period. Sam entirely misses the specific command word requirements, things like evaluate or analyze. Both of these approaches completely fail to hit the higher order cognitive domains of application and analysis that Cambridge strictly demands. You literally cannot just dump facts, and you definitely cannot ignore the command words. Moving right along to section 2, core cache principles. This is where we build the foundation so you don't end up like Alex or Sam. Avoiding those traps we just talked about requires mastering the theoretical architecture first. Cache memory isn't just fast memory. That's IGCSE thinking. At this level, it is a complex theoretical architecture requiring highly precise definitions, clear causal relationships, and, this is crucial, integration with other syllabus areas. This right here is where you separate yourself from the pack. The principal examiner reports explicitly state that candidates who reference cross-topic connections achieve significantly higher marks. So what does that actually look like?
Well, it means when you talk about cache memory, you shouldn't exist in a vacuum. You should also be referencing pipelining. You should be actively discussing how a cache miss completely disrupts the instruction pipeline. You should be mentioning bus widths and data transfer rates. You really need to show the examiner that you understand the fundamental cause and effect relationship. For instance, a larger cache means a higher hit rate, right? But it also means slightly slower search times within the cache itself because of the increased physical size and complexity of the hardware. It's always a trade-off. You have to demonstrate that you get the whole picture.
Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Welcome back. Let's get right into Section 3, the method mark strategy. This is all about moving from pure theory to actual exam execution. In computer science, algorithmic thinking is absolutely required. Cambridge actually awards method marks for the step-by-step process of decomposition rather than just giving you points for arriving at the final answer. The standardized sequence you see on the screen right now is basically your exam safety net. Step 1, identify the key elements in the question prompt. Step 2, apply the relevant core principles. Step 3, execute your analysis and show clear working. Step 4, verify your results. And Step 5, present it in the appropriate format. Now, to make this even more powerful, I highly recommend overlaying this with the Peel framework for your written paragraphs. That's point, evidence, explanation, link. Let's do an example. Say the question is about choosing between L1 and L2 cache for a highly specific application. Your point, L1 cache will minimize instruction fetch latency. Your evidence, it is located directly on the processor core. Your explanation, this reduces the physical distance signals must travel compared to L2, which significantly lowers the penalty of a cache miss during a pipeline fetch stage. And finally, your link. Therefore, for this specific real-time processing scenario, prioritizing L1 capacity is absolutely critical. Do you see how incredibly structured that is compared to just writing L1 is faster? That is how you get full marks. Okay, we are going to put this into practice right now. I'm initiating a 60-second interactive data scan challenge. I want you to imagine you are sitting in the exam room and you are presented with a massive, complex data table showing cache hit rates diminishing as cache size increases beyond 8 megabytes, while at the same time, the manufacturing costs are absolutely skyrocketing. The clock is ticking. You have 60 seconds to visually extract the core trend. Go. All right, what are you looking for here? Don't just stare blindly at the raw numbers. You need to look at the rate of change. The command word for this question might be justify. If you were only looking at the performance column, you'd probably just say make the cache infinite, make it as big as possible. But you have to look at the cost to performance ratio. That's the trap. You've got about 30 seconds left. Start applying the method mark strategy we just talked about. Identify those key elements: size, hit rate, cost. Apply the principle. In this case, it's the law of diminishing returns. 15 seconds. You should literally be formulating your Peel paragraph in your head right now. Point, evidence, explanation, link. 5, 4, 3, 2, 1. Time. Okay, let's break it down. If you realize that the core trend is the nonlinear relationship between cache size and system performance gains, and that beyond a certain threshold, the hardware cost vastly outweighs the computational benefit, then congratulations, you are thinking exactly at an A-star level. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 great boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's keep this momentum going into Section 4. Top 3 examiner warnings. It is time to play Find the Flaw and learn directly from the mistakes of past students. I have meticulously gone through years of principal examiner reports, and I have pulled out the top 3 fatal mistakes candidates make year after year. Mistake number 1, confusing cause and effect. This happens all the time. A student might write something like, a high hit rate causes a large cache. No. Stop right there. That's entirely backwards. A larger cache capacity contributes to a higher probability of a hit, which in turn reduces the average memory access time. You absolutely must demonstrate clear, logical, causal relationships. Mistake number 2, forgetting boundary conditions. Examiners constantly note that students rarely check edge cases. What actually happens when the cache is completely 100% full? You have to discuss cache replacement policies, things like least recently used, or LRU. If you don't actively mention what happens at the physical boundary limit of the memory space, you wave goodbye to your evaluation marks.
Mistake number 3, generic, non-specific answers. Remember Alex from earlier? Rote memorization fails completely here. If the exam question is explicitly about a weather forecasting supercomputer and you just write down a generic textbook definition of RAM and cache, you get 0 marks for application. Nothing. You must tailor your answer directly to the fact that weather forecasting involves massive arrays of sequential data, meaning spatial locality is extremely high, and therefore a larger cache line size would be highly beneficial. Context is everything. Let's move into Section 5, Critical Analysis and Evaluation. This is where we secure those final elusive marks by engaging in deep evaluative thinking. Evaluative thinking basically means analyzing trade-offs. Nothing in computer science is free. I want you to try a speed writing challenge with me right now. I'm going to give you exactly 30 seconds to mentally outline a perfect Peel paragraph on the specific trade-offs of level 1 versus level 3 cache. Ready? Think about physical proximity, overall size, transfer speed, and manufacturing cost. Go. You need to be weighing these options against each other. It's a balancing act. L1 is incredibly fast, yes, but it's tiny and extremely expensive to produce. On the flip side, L3 is a bit slower, but it's huge, and it's shared across multiple CPU cores. How do those facts interact? You've got 10 seconds. How are you justifying your final conclusion based on those constraints? Time. Okay, listen up. If you didn't reach a strongly justified recommendation based on solid evidence, you completely missed the critical analysis mark. Getting that mark means bringing in advanced concepts of time complexity and space complexity. Does increasing the cache size improve the time complexity of the data retrieval algorithm? Yes, absolutely, up to a point. But it simultaneously increases space complexity on the actual silicon die, which drives up manufacturing cost and heat output. You must synthesize exactly how all of these individual factors cumulatively affect the overall system performance. Justifying your recommendations with this kind of multifaceted evidence is completely non-negotiable if you truly want that A star. We've made it to Section 6, the final hack. This is our unified success system, designed to pull everything we've learned together into one actionable strategy. So, you now understand the complex theory, you know the deadly traps, and you've mastered the required structure. Let's combine all of them into a custom mnemonic memory hack so you never freeze in an exam again. When you flip that page and see a high mark question on computer performance, I literally want you to write the word cache down the margin of your exam paper. C stands for context. What is the highly specific scenario they just gave you? Is it air traffic control or a smartwatch? A stands for apply. Apply the core principles and immediately start using your Peel framework. The next C stands for cause-effect. Ensure your arrows of logic are pointing in the exact right direction. Do not confuse the symptom with the underlying cause. H stands for hack boundaries. Look for the edge cases. What happens when the memory is totally full? And finally, E stands for evaluate performance. Weigh those trade-offs, look at time and space complexity, and make a firmly justified recommendation. If you run your brain through this CACHE checklist on every single extended response, you will automatically hit every single assessment objective the Cambridge examiners are ditting for. It's practically a cheat code for your brain. I really want to conclude the core of today's explainer with this incredibly powerful examiner alert, pulled directly from the source material. Always define terms before using them in extended responses. I know, it sounds almost too simple, right? But trust me, thousands of smart students lose easy marks every single year because they arrogantly assume the examiner knows exactly what they mean by hit rate or instruction latency. Do not ever assume. Remember our paleontologist strategy from the very beginning? You have to reconstruct the whole dinosaur from the ground up, starting with the very dirt it's buried in. Define your terms clearly, right out of the gate, build your logical argument step by step, and definitively prove your comprehensive understanding of the topic. Leave absolutely no room for doubt. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCE to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. Before you close this tab, ask yourself this. The next time you face a complex 8-mark question, are you just going to blindly dump facts like Alex and hope for the best? Or are you going to grab your shovel and start digging for those marks like a true paleontologist?